I don't think you've ever seen Professor Ghaffari and me in the room at the same time. We're 6 feet apart and 40 and more than 30 years apart. How about that, Monty? So, wow, we're wrapping up the last days of Rob 101. Monty and I have been having a great time working with you guys. We've got a little bit more of information to share with you, but I wanted you to be able to meet the brain trust of Rob 101. So I hereby give the floor to Professor Chad Jenkins. Chad, they can see you if you're up close to the lectern, so we'll give you space.
All right. I hope I've turned the mic on and people can hear me. So hi, I'm Chad Jenkins, Professor Chad Jenkins. I'm Associate Director of the Michigan Robotics Institute, serving underneath our fearless leader here, Professor Jesse Grizzle, and alongside my good colleague, Monty Ghaffari. And so I just want to say that this really was just a dream that I've sort of had for a long time. I sit in computer science, and we see a lot of students come through computer science, but we know that there's a number of issues in that students want to do robotics, they want to learn interesting things, but they can't really get exposure until their third year or their fourth year. And so this was just a way to say, how can we bring some of these ideas up into the first year experience, make it more accessible, try to meet the demands of students and get them prepared for this new future that we have that's gonna involve artificial intelligence and robotics. And so Jesse, basically heard me just musing about this and said, all right, let's put it into action. And the next thing I know, we're offering a Robotics 101, and it's going through approval process, and we're able to deliver it to you. And so I'm just really grateful to Professor Grizzle and Professor Ghaffari for carrying this out and really doing a great job with it, creating a new book for this class, and just doing amazing things. And it just makes me think that I, to some extent, I'm envious of you because you're getting this opportunity. I didn't realize when I was an undergraduate how important linear algebra was going to be to my career, to everything I do, everything I didn't realize I was going to do in robotics and artificial intelligence. I always tell myself if I could go back to 1994 and talk to my 1994 self, I would have said, pay more attention in linear algebra, and because you're going to be using it, you're going to be seeing these things so often, and it's much more interesting than you realize. And really, we've just sort of, I saw that Jesse put up singular value decomposition. That's not something that I got exposure to, and I was able to learn until I got to graduate school. And so, I wish I would have had that background. It would have made me so much stronger, so much more capable, be able to do so many things. Whether it's machine learning, computer vision, robotics, computer graphics, cryptography, really linear algebra is the basis for all of these. And so I'm really glad that we're getting an opportunity to make this more accessible, make it more useful to you, and hopefully build this out so that we can scale it to more and more students and meet this need. I think it has an opportunity to not just change how we do things at Michigan and create more opportunity at Michigan, but it also has the ability to make it more accessible more broadly. So I'm very grateful to the students from Morehouse and Spelman who were able to participate and give us great feedback and be a part of what we're doing here. And I think this is something that can scale to many more institutions. I think what we are able to do is allow students to be comfortable in their environment while still getting the material and being able to have the opportunities that are just sort of at the cutting edge of artificial intelligence and robotics. I could go on and say so much more, but I just wanted I'll just leave it at that and say how grateful I am to everybody for pursuing this. And what you're really doing is helping us build a foundation for the future. And so thank you again, and best wishes for a safe and happy end of the semester and happy holidays. Thank you very much.
Thank you so much, Chad. So, Monty, what you go
ahead? You want to say a few words if people are asking one-on-one or not really?
Okay. All right.
103, 103.
Oh, I forgot to say that.
A lot of
No,
you guys
no.
want to continue.
Oh.
You're asking us, maybe it's more.
I thank you. So Professor Gafar made an interesting point that I forgot to talk about, which is what do you do next? And so after taking this course, really there are a number of things that you can do beyond this. This is just really an introduction. If you want to do more in robotics, we will be offering a class next semester. It will most likely be Robotics 103. Hopefully also in combination with, that will also be offered as an Engineering 100 section. In that class, that really is about how we can get exposure to the machine shop, understand how we build things, making a platform on your own, of making like a robotic platform. Either would be a differential drive robot with 2 wheels and it moves through the speeds of those 2 wheels, or an omni-drive robot that can move in any direction. But you'll learn how to build those robots, control them, program them at the low level, and then, and so that is really about the building of these robots, how you make the machine. If you want to do even more than that, hopefully next semester, we will offer, not next semester, I'm sorry, in fall 2021, we will offer Robotics 102. Hopefully we can get that through. This is still in development, which is really a path planning course. Just the basics of artificial intelligence, so you can do autonomous navigation with the robots that you build. And you can have them, it's like the same thing that an autonomous car does. You could do that with the robot that you're building. And then there's more and more courses that you can do beyond that. We're building a robotics undergraduate program. We're going to emphasize things like human-robot interaction, human factors, but also and other things like being able to do simultaneous localization and mapping, so your robot knows where it is and it can perceive its world and do computer vision and things like that. We're also, this course, Robotics 101, let's say that you love this class, but you realize that robotics really isn't what you want to do. You want to do other things in artificial intelligence or computer science or electrical engineering. And so, so this class, Robotics 101, the linear algebra of it prepares you for doing machine learning. So if you decided that you want to do machine learning and take that course, or you want to do computer vision, this course really provides a lot of the foundations for doing that. And so we're working to make sure that this course can fulfill your prerequisites for advanced courses and other non-robotics advanced courses in artificial intelligence. And so there's many different directions you can go from this course. I'm always happy to talk more and talk about these opportunities and these options. Hopefully that's that. Thank you for reminding me to say that.
Thank you. That comment.
All right, excellent. Thanks again.
Thanks so much for coming in, Chad. I know it's a lot of work just to come in from home to do this, but no problem. My pleasure. Thank you for running for office. Okay.
And we'll talk more about other stuff later.
Yeah, so I'll talk to Ilya sometime if you have time to make it too, but otherwise I'll.
Was that today?
I'm going to try to do it today. Yeah. Because TechCom's going to go crazy when finally tell them Wednesday this week. Got somebody hearing you.
Yeah, I will so.
All right. Can you guys hear me? Great. So, we had a motivational speaker. Now we're going to talk about a little bit more serious stuff in terms of math. So, we were torn whether to tell you about singular value decomposition or convolution. So Jesse, Professor Griesa prepared singular value decomposition for you in the book. So there's a section in the end, you can read it. And given that he taught you factorization, matrix factorization, and eigenvalue decomposition, that should be possible for you to read through it. That's a general way to factorize a matrix, and it's related to eigenvalue decomposition in case where your matrix is a square matrix. So I decided to go on with convolution because, well, it's something that you will see in computer vision course and many other courses in engineering. Plus, you hear about it a lot. It's good to know what it is. So I'm going to talk about convolution and give you two interesting examples. So I'm not writing today. I'm using some slides and hope that works as good as writing down. I'm going to prepare my pen. Let's see. All right. So convolution is, what is it? Convolution is a topic that most likely you will struggle with it the rest of your life. But here we try to understand it. So first of all, this is a fairly tricky concept. It has a mathematical definition, and it has a lot of applications in engineering. Now, the way I learned it, I took differential equation course. We had a math teacher in undergrad. He taught us continuous version with using integrals, how to do convolution. We did some hand calculations. We really didn't know what to do with it. And then later we learned solving some differential equations. And then until much later, we realized, okay, there are lots of things we can do in signal processing with convolution. So here we start from discrete convolution, because that's what you really see these days. A lot of people use, and I'll leave the continuous version later. You catch up with it in other courses. Okay, so I'm going to ignore the update. So the convolution of an n vector A, suppose we have an n vector A and an m vector B. When you take the convolution of these two, we end up with an n plus m minus 1 dimensional. We'll see why. So we use this notation, use the asterisk to denote that this is not a multiplication, this is a convolution. So we write the convolution of two vectors using this sum that we define here. So we get a new vector. It has a bigger dimension, m plus n minus 1. And each index of C, which we use k, is defined by summing over some elements of A and B, multiplying them. And the indexing rule is that I plus j must be equal to k plus 1. Now this is, following its definition is a little convoluted, but we're going to go through that, and that's the reason it comes. That's why it's called convolution. We're convoluting one vector through another vector, and it's super hard to imagine what's going to be, right? So wait for the examples, then we talk about it. So actually, the 2D example, the visuals help a lot to understand, but the math looks really scary. And the 1D, the summation is it's possible to track it with your mind, but a little hard to imagine, but we will see. Now, so k starts from 1, and then we continue until m plus n minus 1. Now, I want you to tell me why from 1 to m plus n minus 1. There's an obvious reason to do that. Otherwise, you might wonder, why that? Why not something else? I am looking at chat. That's the upper bound for k. Great. because A is n-dimensional, B is m-dimensional, m plus n is, well, the maximum number of elements we can have to multiply if we sum over it. And then because the rule was I plus j must be k plus 1, then if we don't add this minus 1 here, then we're going to go out of the index bound. All right, so that's sort of not obvious if you don't think about it, but obvious once you give it some thought. Okay, so let's do an example. Otherwise, this will not be clear at all. Now, suppose we have a 4-dimensional vector and a 3-dimensional vector. Let's expand that sum. We get C1 equals A1 times B1. This is something, it's worth you write it down and see that this is what you're going to get. And C2 equals A1 times B2 plus A2 times B1. Now, notice that when I have C1, the other side, sum of the indices that I have, 1 plus 1, is always what I have in the left, the index of C plus 1. So if I have 1 here, here I have 1 plus 1 equals 2, which is 1 plus 1 the other side. If I have 5 here, 5 plus 1 must be 6, and here I have 3 plus 3 and 4 plus 2. So we take out every possible combination that we can get from the indices that construct such that sum of them equals the left-hand side index plus 1. If you follow this rule, now it's a little exhaustive. You can imagine if the vectors are long. We don't want to do that by hand. But it is possible to write it down for low-dimensional problems. Okay, so let's do a numerical example. What is the convolution of vector 1, 0, minus 1 with 2, 1, minus 1? So the first one, this is C1, must be A1 times B1. So it's 1 times 2. These two guys here. Okay, so, and the second one is C2 must be the first one times the second one, and then the second one times the first one here, which is what you see, 1 times 1 plus 0 times 2. And if we follow the same steps, and we get the last element, which is C3, 4, C5. Now, let's check the dimension. A is a 3 vector. B is also, this is A, this is B. B is also a 3 vector. The claim was that C must be n plus m minus 1 dimensional, which makes it 3 plus 3 minus 1, 5. So that checks out. Now this is very important because later you're going to hear crazy things like convolutional neural networks, and then people are debating online what should be the size of the convolution, and somebody's saying that that's really not clear. That's the magic that developers put in the code, and you need to write a function to print out the result, get the size in the code, and then go back and put it in your class, neural network class, to know. But if you're an engineer, you know convolution, you calculate it and type it there in your code. You don't do those sort of hacking. It looks bad on you if you post your code online. But also, they're genius because they have no idea, still they figure out to solve it using just coding and hacking. So both are great, but it feels great to know why things are the way they are. All right, properties of convolution. It's symmetric, which is great for vector spaces that we talk about. A convolution of A and B is the same as convolution of B and A. And it's associative that if you have convolution of A and B with C, so we first compute A and B and then compute the convolution with C, it's the same as if you compute first B and C and then take the convolution with A. This is really good because when you implement it, there's little chance you make mistake by changing the order. And another property is that if the convolution of two vectors is 0, one of them must be 0. So there's no way if the convolution is 0 and A and B are not 0. All right? Now, related to what we do, can we write down the convolution as a linear map? Remember, recall linear map was any transformation that we can write it as a matrix. And when we multiply the matrix by a vector, we get another vector. And it's very convenient to implement it in a computer using linear algebra libraries if you have a matrix. It turns out that's possible. We can write down that summation notation, which is fairly hard to track, using a matrix that actually makes it super easy to remember. If you look at it, let's say the right way, which is my way. I'm going to tell you. Okay, so convolution of A and B, because it's symmetric, we should be able to transform B into the matrix or A into the matrix. And both ways should be fine. Let's see how that works. So we know already that the output, the vector that is the result of the convolution, must have n plus m minus 1 dimensions. And t times, you know by now that t times a, if a is n by 1, and the output, which is C, is n plus m minus 1, obviously T is n plus m. I don't have enough space. Oh. So T is m plus n minus 1 times n. A is n by 1. Because we want the result to be m plus n minus 1. So that much is easy to guess. Now the question is how to fill the matrix. Well, somebody had to look into it and see what makes sense to map that summation into, or the expanded version that we have, into a matrix, and then we do induction and realize if we go to a very large indices, whether that holds in general or not. So this is the rule we see here. Now this is, I know it's not super easy to remember if I give you this, but again, you can look into this, see if it makes sense using the indices. There's a little index gymnastics here you have to track. But what I want to show you is that when we put it in a matrix, which that rule is true, super easy to remember, because what I'm going to do here to point out that to construct the matrix that is a convolution map of vector B, we start with putting, now we know, remember, we know the dimension of the matrix. We can initialize it using matrix of all zeros, and now we just need to fill in. So we start from here, and we just put our vector B here, right? Next one, move one step forward to the right and bottom to go to the next diagonal element. And then put your vector B again here. Same vector, just repeat it. Do it again. Vector B again.
Shift left, shift down.
Right. So if you played ever Mortal Kombat, you should be good at this. When you do fatalities, you can the cheat codes are like this. That was my childhood game. That's why I have a temper now. I played that early on. So, but how many times we repeat this? This is obviously n times, right? Because remember, b was n plus m minus 1 times n, because we want to have the same columns in T as the same number of rows in A, so we can multiply them. Otherwise, it's just the syntax doesn't make any sense. So that's easy because we know how many times we should repeat this process, and it's actually programmable. We can code this just the way it is to construct T. Similarly, for A, we can do that, but now we have n plus m minus 1. The output must be the same because, remember, the result is supposed to be the same no matter if we take the convolution of A and B or B and A. However, now we have to repeat it m times, and we repeat vector A here. All right, so I much prefer this way of remembering it. I need to think, I need to take a moment and think about that summation. I have to admit I still struggle with, maybe other people do, but nobody talks about it. So physicists do that. They write matrices as double sum, triple sum, and they're horrible. I do not like them. The summations, not the physicists. I like them. So I think matrices are much more understandable because we can see the structure. And by the way, this is a structure. When you hear there's a structure in this matrix, because it's not a plain and boring m by n or n by n matrix with a bunch of numbers. There's a structure, and this is structure here, you see? This is called a band diagonal matrix. Now, it can be shifted up and down, but there's a band of numbers along the diagonal, and everything else is 0. Okay, and there's a name for it too. If I say it correctly, it's Triplets. It's a German name. But the mathematician was Otto Triplets who invented this matrix. So we call this Triplets Matrix when we have this structure. In fact, we have a function in some linear algebra matrices to take a vector, put it in a matrix like that for you. Now, I'm not going to use it today, but I know MATLAB has one. I haven't checked in Julia. Okay, in control engineering, you see this matrix when you want to do preview control. You want to predict a lot in future in time. You make a lot of replicate of your command, and then you shift them like this in time steps. That's what they do. They call it preview control. But anyway, we're talking about convolution and signal processing here. First example, time series. We want to, the idea is that I have a signal, and, well, time series is a signal that is evolving over time. We track the values of the signal over time. For example, a stock market that you see, you had some stock going up and down like this, then we had the pandemic went down, and then some stocks moved up again. It's never smooth, it's like this. And well, that's just how it is. It's very stochastic, noisy. It goes up and down. Now, a lot of times these apps and plots that you see, they provide some moving average or some way of filtering this noise. You want to see the trend. The trend of the value, maybe it's like this line that you see here. Because it doesn't matter if it goes up and down, over a window of time when you look at it, there's a trend in the signal, and that's the trend that we want. And then you hear a lot, and this is in our everyday speech as well. People tell you that separate the signal from noise, right? Well, the signal means this is the content of that basically information that we get is the trend of it. Now, anything around it is the noise. We would like to be less sensitive to that. We don't want to pay too much attention to the noise, and we want to pay attention to the trend. Now, translation of that in this example is that you don't want to trade the stocks every day. As soon as it goes up and down, you want to just leave it and forget about it probably for a while, look at the trend. And then over maybe 1 year or 2 years or 5 years, when the trend goes up, maybe you want to now make decisions. So that's the idea, and time series are very important in financial studies. Banks are super interested, insurance companies are super interested in this. Engineers are interested in this because we can predict in the future. That's very important for artificial intelligence and robotics to predict in the future. The example I have here, we are not going to details about what is a normally distributed noise that I'm adding here. You need to take a signal processing course, and hopefully you will enjoy it more once you know that you have a lot of real-world application to try. I am just generating a signal here. It's a sine wave curve. It's a sine of t minus pi over 3. So t is time. Let's say seconds or anything you want. And this is a noise corrupted version, right? So we have the actual signal f, which is blue, and then I have a noise corrupted signal. The signal is corrupted by noise. This can be a wireless communication channel. It's a radio, you send your signal, the receiver is getting the signal, but it's noisy. Imagine you want to put some filter to remove noise and you can hear the voice more clearly. We can use convolution to do that. So the idea is that ultimately our function is a very long vector of values, right? That sine wave that we had is a very long vector of some values that we receive. Let's call that y. And we talked about convolution of two kernels. Now, one of the two vectors, one of the vectors is my signal. It's a noisy one. The other vector, which we had a and b, the other vector is arbitrary. It's the design choice. Let's say if I pick k to be a 3 by 1 vector, and each of its entry is 1/3. Now, the convolution of this k, we call it kernel of the convolution. It's the convolution kernel, or kernel of the convolution, is something that I can use to filter that signal. And we will see how it works. So I take the convolution of k with y, and I get a new signal, g. Now, what is the result? Let's say y is n by 1. It can be very long, right? So you can have 1,000 values, 10,000 values. And then k is 3 by 1. G is n plus 3 minus 1, which is n plus 2. So I end up with an n plus 2 vector. What does it mean? Now, the idea is that if I have my signal, and imagine I take this K, and the window size is 3 time steps. And I move this every time. It's a discrete time signal, so I go with 1 step at a time, right? Each time, I should use different colors. Oh, here. So I'm going to shift this 1 step forward. Now I have this. Then I get 1 more. 1, 2, 3. So I go all the way here until the last part. Now, obviously, in the end, I don't have enough elements in the signal, this convolution, that's why increasing it, right? So this is what it's doing is taking a moving average. If you write down the definition of the convolution, what happens here, I am, within each window of time, I'm taking 1/3 of that element here. So 1/3 of this, 1/3 of this element, and 1/3 of this element. And then add them up and divide by the sum of these elements. But because it's normalized, it adds up to 1. It's really the same thing. So this is very intuitive now. So at any time, let's take the value before it and value after it and average based on the weights that are 1/3, equally weighted. So I could change the weight. I could say that I'm going to get 2/3 of this one, maybe 1/6 of this one, 1/6 of this one, right? So I want, wherever I am, I want to put more emphasis on that and then pay some attention to the previous one and the next one, and then take the average. This has an effect of taking the weighted moving average, okay? So this is what really the concept you should imagine in your mind. That I have a signal, I take, in a discrete time, I take a kernel, and I move it over my function. And that kernel will do some processing over my function. And what is the nature of that processing? That comes down what is inside the kernel. Those numbers are important. Now, I'm going to relate it to differentiation. Suppose the kernel is -1, 0, 1. If I apply this convolution to my function, which is really just multiply each element of the function with that kernel and basically add them up, I will get, let's say this is index 1, 2, 3, right? This is same for my function. In this window of time, I get f of 3 minus, this is 0, will cancel out, f of 1 and divided by nothing, but I could just do maybe 1/2. I think it's okay. So we can leave it like that. So now you can see that I'm actually calculating delta of my function. By moving this convolution kernel over that signal, I'm taking that delta. But I'm not taking delta between, say, k1 and k plus 1. I'm taking a delta between k minus 1 and k plus 1. That's sort of skipping one element. So you have a lot of freedom what to do, and you can construct, for example, differentiation kernel or some other applications that we'll see in the next example. So this shows the generality of the convolution. And now I'm running that kernel. I want you later to go through this example here. I'm constructing that matrix, which what I'm really doing is just filling each. I'm writing a loop over the columns of my T matrix, and I'm filling in with the vector. And here, because my convolution is now matrix multiplication, now this is just a matrix multiplication in Julia. It looks like that convolution operator on the paper, but it's not. And with a simple matrix multiplication, I'm computing my convolution. Now what happens, I can, you see that I can get a much smoother signal. This is really basic. We're not doing something super sophisticated. This is my kernel here. But this is still better than just working with a noisy signal, okay? So this is a one-dimensional example. And I will give you the notebook I uploaded on lecture notes today. Let's talk about 2D convolutions. Do you have any questions from the one-dimensional case? I think the intuition is more important now than the mathematics that we went through it. Okay, so the 2D convolution is just generalization of what we talked about to a 2D plane, 2D space. Instead of one sum, we're going to have double sum here. But we apply the same rule. So across each dimension, we do exactly what we talked about. Now, because it's a 2D space, we have to do it for each dimension. And then what it ends up to be, because it's a double sum, for each index here, we have to go over all the other indexes of the other sum. Pretty convoluted. You can always say that. It works on so many dimensions. All right, so, and then because we don't have any notation, we will use this to highlight that this is a matrix, but you don't have to. Excuse me. Okay, so I have a very cool example here. Oh, just one point is that just like the previous case, the dimension is, this is more important to know because this is what you actually see in convolutional neural network examples. You need to set the dimension of a possibly 2D or 3D array. And if A is M by N and B is P by Q, you get across each dimension, your dimension will increase to M plus P, first one with the first one, right? M plus P minus 1 and N plus Q minus 1. So this is the rule you can use to know what will be the output, the dimension of C, if you apply the convolution of A to B. Now we're going to look into an example that is very practical in computer vision for edge detection. I have an image, I want to detect the edges in the image. Just like before, we need to pick something that we call convolution kernels. But here we can talk about convolution kernel along each dimension. One is along X, the other one is along Y, or rows and columns. So the idea is that if I apply these convolution kernels to my image, it should give me something that is useful for detecting the edges. Now, these particular kernels, there are many kernels. I'll show you some page on Wikipedia that you can read more about it. And they have names sometimes because somebody used them first or introduced them first. These two kernels are called Sobel Kernels. Sobel kernels are usually used to take the image gradient. So there are several kernels that you can use to compute the gradient over the image. It's the same gradient, we talked about it. It's a numerical method to get the gradient. And you see it has different weighting. For the middle value, it takes weight is 2. And for the one before and after, the value is 1. And what it's really doing is taking the difference between one element before, one element after, and the element you are at, and the weight the one you are at twice as the other ones. And that will give you some delta over your image. Okay, so, and we do the other thing along the other dimension that you see is sort of flipped, it's rotated. Now we have, instead of 1, 2, 1, we get 1, 2, 1 along the rows. And in the code, we will see that it is flipped because I'm bringing the negative ones here. That's just because if you track the summation, that makes more sense in the code, which is a practice for you to go through it. But you see the kernel is defined like this. This is called Sobel Kernel. Sobel Kernels. All right, so now the idea is that if I apply kx to my image, two matrices, we take the convolution, that will be the image gradient, derivative of the image along the first dimension x. And if I take the convolution of ky, the second kernel with the image, I get the other gradient along the other dimension. Now, if you take the norm of that gradient for each pixel in the image, you have the magnitude of your gradient, which we can use it to get edges in the image. We want the intensity of the gradient, the magnitude of it. Let's make it more clear. Here we have the image of Fabio. I don't know him personally, but in test images of Julia, if you load test images of Julia, it's a package here. You get a bunch of images you can try. I just picked one of them because faces have a lot of features. People use usually human pictures to do edge detection. It's a pretty complicated with shading and everything. Okay, so now I give you some more intuition because in computer vision, the coordinates are like this. They call them x, y, or sometimes u, v. This is your 0, 0. 2 minutes. This is 0, 0, and we start, let's say, an image is really just an array of number. You have an array of number here, and each pixel has a value between 0 and, let's say, 255, or sometime between 0 and 1. So my kernel, which is 3 by 3, it moves like this, right? I just move the kernel all the way here. Then I start again here, and then move it. So I take the kernel, I just go over the image and do whatever I want to do. And that kernel will, I do it twice for x and y. And that's the convolution. And that's what you see in convolutional neural network. That's exactly what they do. Now, you will learn in computer vision and deep learning, they will learn what are the weights inside that kernel. That's the power of convolutional neural network. They learn features in the image because they can find the kernel that gives you the best features. Whereas if we do hand design, we don't know what are the weights inside the kernel. So that's something exciting to learn. And this is the code I'm using to detect, I call it Sobel edge detection. I define my kernels, and here I'm doing some magic. You see, for each block of the image, I am applying element y as my kernel. We're out of time. And in this line here, you see that I'm saying it's a ternary operator. I'm saying that if the norm is bigger than this threshold, take that value. Otherwise, well, if this is true, take this value. If not, then take this value. That's the meaning of it. And let's see the results, and we're done. And this is what you get. These are the edges we detect using that. And with that, we're going to end a great semester with you guys, Rob 101. It's been really good. It's been educational for myself, too, because re-explaining all these topics as a freshman course taught me a lot. I'd like to thank every one of you who were patient and stayed with us.